Good morning.
Good morning.
I'm Juan.
I'm Jaden. I'm Emily. And this is our E84 Final Project. Our project is building an
Electromyography.
sensor circuit that detects and amplifies electrical signals made when you contract your muscles. People can use these circuits to control devices by contracting and uncontracting their muscles, allowing them to do stuff like play video games with them. So, this is a schematic of our circuit. Our circuit contains a difference amplifier meant to extract the muscle signal by finding the voltage between two inputs detected by electrodes. This is shown as EMG1 and EMG2. Next up is a high-pass filter to remove the DC component and get rid of any signals at low frequencies. Now we have a precision full-wave amplifier, a low-pass filter, an inverting amplifier, and another difference amplifier. Next, we will explain how we set up our circuit and what each component does. The voltage from EMG1 and EMG2 is very small, meaning we need a large gain in order to properly read these values. Using resistor values of 1 mega ohm and 10 kilo ohms, we were able to create a gain of 100. This is a picture of our active high-pass filter. This allowed us to block the DC signal that results from the existing difference of potential between the two electrodes when the muscle is at rest. We also use resistor values that would give us a gain of 15 to amplify the signal. We were able to use impedance to find the gain and the cutoff frequency. The purpose of the precision full-wave rectifier was to convert the AC signal from the high-pass filter to a DC signal. We used a precision full-wave rectifier instead of a diode bridge rectifier because the weak signal from EMG1 and EMG2 would not have been greater than the threshold voltage of the diodes, which is typically 0.7 volts. The advantage of using the precision full-wave rectifier is that it uses the op-amps to ensure that the diodes have no threshold and zero resistance. After calculating, we found that all the resistor values would be equal to 10 kilo ohms, and Vout can be expressed as the absolute value of Vin. The low-pass filter helps filter out high frequencies since the frequency at which humans can reasonably control muscles is relatively low, so only low frequencies are important, and high frequencies can be ignored. We use adjustable amplifier to make Vout positive again using a negative gain. This is because the voltage from the low-pass filter is negative. Similar to the adjustable amplifier, the resistor in the offset selector is shown as a potentiometer, allowing the voltage to be anywhere between the lowest and highest potentials. And finally, many people who build these circuits use a final difference amplifier to be able to increase or decrease the output voltage depending on the device they wish to control. This is most often a console. This is a picture of everything assembled. 2 electrodes are connected to the subject Jaden, and 1 is connected as a reference to our other subject Juan. The circuit output is connected to an oscilloscope where we can see the trace while the muscle is flexed versus unflexed. Now, I'm going to talk about our results. As you can see from our video and the oscilloscope traces, the EMG did respond to muscle contractions, but this was shown by a noisier trace rather than a significant change in the amplitude of the detected signal. We also noticed that electrodes with a firmer and larger foam sticker were able to detect better signals than gauze pad electrodes. These stronger and larger foam stickers were used in this video. One main source of error can be the quality of signals that we are receiving. The EMG signals we get in general are very weak. Additionally, we do not have much information about the sensors that we are using because they came from the analog lab. The human body's own electrical movement can also impact the reading of the signal. Furthermore, we are also not sure if the placement of the electrodes that we chose can provide us the best quality signal. The values of the components we use may also be slightly off from their labeled values, and the error can get amplified through the op-amps. Further improvements can be made by finding a way to amplify the signal only when the muscle is contracted. This could be achieved by adding a low-pass filter since the signal created by muscle contraction is at low frequencies. The original high-pass filter removes the DC component, so we only focus on the small variations in the signal we get from the muscles, and these small variations can be amplified such that it's more noticeable when there's a contraction. Through this project, we were able to see and experiment with different types of filters that we went over in class, and we gained a better understanding of their purposes and effects on the signal. Through the calculations, we were able to solidify and use formulas we saw in lectures. we learned the effects of placements of electrodes on the subject's arm. For instance, placing the electrodes on the inside of the forearm shows a clearer signal than placing them on the biceps.